thank you so much for coming. This is maximizing database performance with isolation levels. We're going to talk about transaction isolation in all of the SQL Server and Azure SQL DB and managed instance and everything else products and why they matter and how you can perhaps find bottlenecks or increase the performance of your applications by investigating and understanding transaction isolation. So very quickly about myself, my name is Bob Pusateri. I am been working with databases for over 15 years now, based out of Chicago, do a lot of work with the community, have been very happy to be a volunteer here at BITS for several years in the past, so this is great. Probably the best thing on this slide is my contact information, so if you have any questions that we can't address during the session, or if you're watching a video of this later and you want to reach out, feel free to catch me on Twitter or X, or send me an email, or you can also find my info on my blog there. As with all sessions, feedback is appreciated. All the speakers here are looking to perfect our craft and improve our presentations, and I'd appreciate any feedback you can offer. If you thought it was great, that's awesome. If you didn't think it was great, that's fine too, but if you could offer some criticism, constructively perhaps, in the forum, that'd be great. All right, so our agenda is pretty simple at a high level. We're going to be talking about the basics of concurrency in general, and then how it actually feeds into the isolation levels that are offered by the SQL Relational Engine. All the materials for this talk, all the slides and the demo scripts and the references and everything else are available either at that QR code or sqlbob.com/dirtyreads. I will have this available again at the end as well, so if you want to get it at the end, that's cool too. So we're going to go back to computer science class for a few minutes here, just talk about what is concurrency, right? Concurrency is the ability for an operation to be broken up into smaller parts or chunks that can then be worked on independently of each other, perhaps at the same time. The ability for multiple operations to access a modify or shared resource at the same time, and the more parts you can break it up to and work on at the same time, well, that means you have more concurrency, and this is all well and good until some kind of limiting factor appears. So there's a famous computer science problem that was proposed by a rather famous Dutch computer scientist, Dijkstra, and he taught this actually, it was like the early 1950s, but he proposed it. It was called the dining philosopher's problem. As you can see on the screen, we have 5 philosophers sitting around a table. Each has a bowl of, in this case, pasta in front of them, and there are also 5 forks. In order for a philosopher to eat, well, you need 2 forks. You can't just have one. But they can only pick up 1 fork at a time, and when they're finished, both forks have to be put back on the table. And if a philosopher isn't eating, a philosopher is thinking. Okay, now, what happens if everybody picks up 1 fork? Well, then no one can get a second fork, and you would have some kind of, effectively deadlock, right? So we might need some kind of rule, like a time limit. Maybe once you pick up 1 fork, you have to acquire another fork within a period of time, or you have to release the fork that you had already picked up. What if some philosopher never ever gets to eat at all? What if they never get their food? They starve, literally. The term is actually starvation in computer science scheduling terms. So we can very easily, of course, translate this to databases, right? Instead of the dining philosopher's problem, this can be the database problem there. We still have our table there sitting around, not a data table yet, but instead of philosophers, we now have end users. Instead of bowls of pasta, we have data tables or data in general. And instead of forks, we now have locks, right? So this is very easy to understand. We have the same problems with multiple users accessing a database at the same time. These are very real problems. Now, some of these problems we can describe by what are called concurrency conflicts, right? There are 3 that are defined by ANSI. They are known as preventable read phenomena. They are dirty reads, non-repeatable reads, and phantom reads. And we'll discuss exactly what those mean in the coming slides. There's also 2 other things we'll touch on very quickly. Those are lost updates and deadlocks. And it's important to note at the bottom of the slide that ANSI specifies which behaviors are allowed at different levels of concurrency and isolation, but not actually how to implement the solutions. So we'll talk about the Microsoft-specific solutions, again, that SQL Server and Azure SQL DB are using in their implementations. The first is dirty reads, right? And this is where we're reading data that is not yet committed. So this is quite possibly data that was changed by another process and is still in flight. It was not actually committed. You can end up, as a result of dirty reads, and we'll see this in a demo in just a minute, you can end up reading data multiple times or not at all, actually. Usually the reason for allowing dirty reads is because some people believe it's faster. The problem is you might be getting a less accurate result as well, so you kind of got to weigh those 2. Next are non-repeatable reads or inconsistent analysis. This is where you have multiple queries that are in the same transaction that end up getting different results. This is the result of a transaction from another process committing some changes between multiple reads that you're doing. The third is phantom reads, and this only affects queries with a predicate or a where clause. The idea is that the result set membership will change. So if you have multiple queries that use the same predicate in the same transaction, they can return differing results. There are, like I said, lost updates or an update conflict. This is where you have one user's update that overwrites another user's simultaneous update, and it has to be simultaneous, right? If I have an update that I do and then milliseconds later someone else does another update, that's not simultaneous. That's just a high transaction load application at that point. But if you have two simultaneous updates, it could possibly, if there is an update conflict, end up being that the first update never occurred or appears that way. And it's important to point out that the SQL engine will not permit this in any isolation level, so it's not really an issue. I just wanted to bring it up here for completeness. Then we also have deadlocks, right? This is where you have two or more tasks that end up blocking each other, and I'm sure we've all probably encountered a deadlock at some point if we've been working as a DBA for any amount of time. You have two or more processes, each has a lock on some resource but needs a lock on another resource to be able to continue, and no work is able to be done by anybody because of this. So SQL Server has a deadlock detection system where it can detect them, and it will choose a victim and roll it back in order to resolve it. The victim is usually going to be the one that is has made the least amount of progress, and hopefully by rolling it back, enough locks will be released that the others will be able to clear themselves. Now, there's a bunch of different ways to address these issues. The two big families here are pessimistic and optimistic concurrency. If we're being pessimistic, then we're expecting conflicts to occur, and we're going to use locks to try to prevent those conflicts. So this is where you get the classic idea of readers blocking writers and writers blocking readers. If you're using SQL Server before SQL 2005, pessimistic concurrency was your only option. I hope nobody here is still using SQL Server from before 2005. But in 2005, they released optimistic concurrency, and this is where we're being a bit more optimistic, and we're saying conflicts may still be possible, but we don't think they're that likely, so we're going to use less locking. I am not saying there is no locking. There is still some locking that goes on with optimistic concurrency, but the idea is we're going to use less locking, and we're going to use something called the version store to try to resolve that. And again, we'll see this when we get to the demos. So with that, we're done with the education part of this, and we're actually going to dive into isolation levels. But before I get there, do I have any questions? Nope, no questions online? Okay, cool. All right, plow right ahead. So as I mentioned, there's pessimistic and optimistic concurrency, and SQL Server has 6 different isolation levels that implement these. So there are 4 pessimistic levels and 2 optimistic levels. Now you'll notice I have read committed, I say default. This is because if you just install or spin up a SQL Server out of the box and don't change anything and create a database, that database will be in the read committed isolation level. That's what they give you out of the box. You can change it to be read committed snapshot instead, and then that will apply to everything in that database. The other levels you have to specify implicitly, or explicitly rather, to be able to make use of them. Now, if you're curious how to tell what isolation level you're in, if you're not sure, first of all, if you're not sure, it's probably going to be read committed, but if you really want to check, you can run a command called dbcc user options. It will give you a bunch of information about the current connection. So if you're using Azure Data Studio or SSMS, each window, each tab you open is a different connection. Each one could have a different isolation level if you altered it. But one of the ones that it will spit back there, as you can see at the bottom, is your current isolation level, if you don't know. If you need to change an isolation level, the syntax to do it can be set at either the connection or the query level. You cannot change it server-wide. And as I said, default is read committed. If you want to change it beyond that, you can use this syntax at transaction isolation level. This will apply the change to all the queries going forward for the current connection. If you open another connection, another tab, what you just did here will not apply. You'd have to do it in the other window as well. If you want to apply it at the query level, this is where you use hints, right? So probably the most common one you would see is with no lock, which means to use read uncommitted instead. You have to apply this on a per table basis. This is a table level hint. So if you're joining multiple tables together in the same query and you want to use with no lock, you would have to actually specify it every time you mention each table in the query if there's multiples. So in pessimistic concurrency, as I said, we're being pessimistic, we're assuming problems, and we're going to use locking to prevent them. This is, again, the classic model. So readers do not block readers, right? You can have multiple processes reading the same thing at the same time. They're not going to interfere with each other. That's all good. But everybody else blocks each other, right? Readers block writers block readers, and writers, of course, block other writers. And once again, we're expecting problems. Now, very briefly, just to talk about locks and what this actually means with the blocking here. There are a whole lot of different lock modes in SQL Server. The lock engine is rather complex, and if you go to the documentation, you can pull up a nice, confusing matrix like this with all the different locks and whether or not they're compatible with each other. I'm going to try to simplify this a little bit, so I'm only going to talk about two of them today, really. Those are going to be S, or shared locks, and X, or exclusive locks. Again, there's a bunch of others. Some I'll mention in passing, but for everything else, we're just going to talk about shared or exclusive locks. Now, locks exist in a hierarchy in the SQL lock engine. So there's 4 levels. There's the database level, the table, the page, and the row level. And just to show, if we do a read operation, so let's say we're running just a simple select query from a table, there's going to be a shared lock at the database level, and this shared lock basically just means I have an open connection into this database. I'm doing something, don't drop this database while I'm doing it. You ever try to drop a database, you get an error that there's a user connected to the database. It's because of this shared lock. Now, because we're doing a select, it's going to be selecting rows, of course. There's going to be what are called intent shared locks at the table and the page level. And what those mean is there is a shared lock at a level below that. And the level that's going to be at is the row. So in order to be able to read a row, we need a shared lock on a row. We're going to have intent shared locks at the page and the table level as a result, and then we have a shared lock in the database just because we're doing something in the database. For a write operation, for insert, update, or delete, we're still going to have that shared lock. Again, everything gets one. At the table and the page level, now we're going to get either an intent exclusive lock or an intent update lock. And then at the row level, we'll get an exclusive lock or an update lock. So, of course, if we're updating a row, we need exclusive. The intents are because the exclusive is at the bottom, etc. Now, the update lock was introduced in SQL Server 2008, I believe, and it was made to help things play a little nicer in the sandbox. The idea here is, let's say we're updating 1 million rows that already exist. We're going to need 1 million locks to make that happen. And yes, there's lock promotion. We're not talking about that. Let's keep it simple. If we need 1 million update locks to make that happen, we might not be able to get all those million update locks or those million exclusive locks right away. It may take some time. So while we're acquiring all those, there's exclusive locks sitting out blocking other processes from doing anything at this point. This can be bad, especially if it takes a lot of time. So the idea here was, instead of acquiring an exclusive lock immediately, you can acquire an update lock. And that will allow other processes to continue doing whatever it was they needed to do. But as soon as you have everything you need in an update lock form, you can immediately promote that to an exclusive lock. And you're not blocking as much. So this is just kind of, again, how the locking will work for these operations. Any questions yet online or in the room? Awesome. All right. So let's dive into our actual isolation levels. First one we're going to talk about is read uncommitted, or no lock, as many people know it. You'll notice I have a little chart here in the upper right-hand corner of these are the preventable phenomena as specified by ANSI and whether or not they can occur at this level. So read uncommitted is kind of like the Wild West. You can have dirty reads, you can have non-repeatable reads, and you can have phantom reads. As a result of this, you may read rows multiple times. You may read rows 0 times. You may return results that were never true at any point in time because they were the result of data that was, processes that were never committed, right? And I'll also point out this only applies to select queries. There was a bug in SQL Server 2008, RC0, I think, where if you used no lock on an update query, it could actually cause corruption. That has long since been fixed, so, patch your stuff. But if you're doing any kind of data modification query, if you're doing insert, update, delete with no lock, congratulations, you're doing absolutely nothing, right? I've seen places where they've had, all queries must use no lock. Okay, well, it's doing nothing here, So I wanted to try to explain no lock in a picture, and what I came up with was a time-lapse picture, right? This is the shutter on this camera was open over a period of several seconds, and we have, the pool balls are both racked and flying around the table because someone broke in pool while the shutter was open. What you're seeing here in this picture never actually happened at any point in time, right? There was never a point in time where the balls were sitting there racked up perfectly and they were flying around. That's not possible. Physics won't allow that. But because this picture was taken over a period of time, it's what it shows. So this is kind of like read uncommitted. Read uncommitted can, again, because it can return results that were never actually committed, it can return something that was never true. So some more myths on read uncommitted real quick are that, well, it's called no lock. That means no locks are taken. This is wrong. That means no shared locks are taken when reading the data. Other locks are taken as normal, and that shared lock on the database is still taken too. The other myth potentially is that it can make a query faster. This is kind of wrong. If you had a query that was blocking on lots of select statements, it might help. But usually your cause of your query is going to be slow is probably something different. So with that, let's dive into our first demo here. So I have a database that I'm going to restore, and this is a database just of US zip codes, so postal codes. And I realize in a lot of the world, postal codes are nice and they use letters and numbers. We in the US only use a 5-digit number. So just to show you what this table looks like, it's really simple here. I'll just query from it. It's literally just 3 columns. It has the zip code and then just the city and the state. Okay, and cities might have more than one zip code if they're large. So the first one here in New York actually has 2 different zip codes because it's big enough. Amherst, Massachusetts, which is a university town, has 3. So there's a many to one between cities and zip codes, or zip codes and cities rather. But that's what this table has. That's all I'm going to do and work with. So if I wanted to just query and say how many cities in the US are named Paris, well, a whole bunch, right? Paris, Maine, Virginia, Mississippi, there's Paris, Kentucky, which is apparently bigger. It has 2 zip codes, etc. Is this big enough for everybody to read comfortably in here? Okay, cool. All right, so we're going to see some dirty reads in action now. And what I'm going to do is I'm going to begin a transaction, and I'm going to update all the zip codes just to be Bob. Boom, okay, now I did not commit this transaction, right? So if I go to another window, if I open a new query, and I select with no lock, well, with no lock is going to return, in fact, that all the cities are named Bob, right? Now remember, this is still an open transaction. This has not been committed. And in fact, whoever issued this transaction is going to realize they made a mistake and roll it back, at which point the results, once again, will change. But if you ran a query with no lock during that time, you just got a whole bunch of bad data that was never actually committed. So that's what I mean by it can return things that may or may not ever have been true. The other thing I'll show you real quick is that the idea that no locks are taken at all, and that it's kind of false. So I'm going to change to my correct process number here. I'm going to spin up an extended events session just to show a lock being acquired. And I'm going to select star from zip codes with no lock while this session is running. And then we have our results here, but what we really want is the extended event results. So I'm going to process these very quickly. Pardon me. And show you that during the time of running that query and selecting star from the table, there were really only 4 locks taken the whole time, and 3 of which were just a shared lock on the database showing there's an operation running in the database, and that SCHS you see, that's called the schema stability lock. That means do not change this table while I'm reading from it, so don't try to add a column or something. It would block on that. Those are the only locks that occurred. So the data itself was never locked while it was being read. There were no shared locks on the data. All right, any questions on that? Okay, that's the end of this demo. We'll go back here. So just to confirm, read uncommitted isn't terrible. It exists for a reason, but you and the business really need to understand the risks and consequences of using it. If you're acceptable with getting data that may not be accurate all the time, it might be worth the trouble. Otherwise, perhaps not. But this is, a business level decision. Make sure they're aware of that. So next we have read committed, right? Again, this is the default, and we get a guarantee with read committed. We get a guarantee that the data we read is committed, right? So there will be no dirty reads. I've again reflected that in the top corner there, but no other guarantees. Okay, so the way this works is, of course, by locking the data while we read it, but the catch is that the lock is only held as long as the read is occurring, and it's released immediately after. So if each one of these boxes here is a row, the row that's currently being read is locked, but the ones that have already been read are unlocked, and the ones that are not yet read are also unlocked. All right, so it's essentially locking a row, reading it, unlocking it, and moving to the next. So to go back to photography, let's talk about a swing lens camera for a moment. Has anyone here ever heard of one of those? I'll describe what it is here. It's a camera where literally the lens can swing. And they were very good for taking panoramic photos, right? Because the lens would actually turn, you'd get a real wide picture. Okay, we do this now, but we do it with our smartphone, right? We just move the whole phone and we can take a nice, really wide panoramic. Same idea, except this was in a camera where the lens did that. Now, these were pretty popular when I was a kid. At least in the US, they would always take on graduation day, they'd get the whole school and the gym or the graduating class and take a nice big class photo with one of these swing lens cameras. In fact, I have one here from my high school, but it's a little before my time. Hang on, why isn't that moving? There we go. All right, so I'm not in this picture, but this is actually from my high school, and it hung on the wall in the high school, and it was kind of legendary because there was a guy in the picture who decided to make use of the fact that we have this lens that swings from side to side. So we have this dude over here who, while the lens was swinging, managed to make it all the way over there and get in the picture twice. Okay? He's even got a nice little smirk on his face, like, yeah, I totally did that. So this is what you can do with a swing lens camera. Unfortunately, in read committed mode, we can also do the same thing with our data, right? Because if the only row being locked is while it's being read, well, then the other rows can totally move around, and there's nothing that's going to stop them. So let's see what happens here with a demo of this. Let me go and close this. All right. So I'm going to re-restore my database just to have a fresh copy here. And I'm going to add an index. So I'm just going to create a unique index on the zip code column, and we're going to run some physical stats just to show you the size of the index here. There's a total of 41,437 records in this data set that I have. So first of all, let's look at what kind of locks are taken, right? I'm going to begin a transaction. I'm going to select the zip code, so it's just going to read from that index. And then I'm going to, while the transaction's open, I'm going to look at sysdm_tran locks, see if that shows me anything for the current session. Okay? Doesn't really show anything, right? All it shows is that one single shared lock on the database. This is because by the time that query had run, that statement had run rather, the locks were all released at that point. So that doesn't help us with anything. So we're going to do the same thing again, but we're going to do it with extended events now and trace this particular session. Now I'm going to try it to detect both lock acquired and released events. I'm going to start this session up, and I'm once again just going to select the zip code column so it reads from that index. Okay, I'm going to process my results here and show you what we get. So there's a whole bunch of things going on. There's some locks that initially get started, but when we get down to it here, and I'll zoom in so you can see, this is, what do we got here? We got lock acquired, lock released, lock acquired, lock released, and the resource 0 is the page number. So lock acquired, row 401, right? Lock released, row 401, acquired, row 402, released 402, etc. So this is the way it is going through and reading, locking, unlocking, and reading. So we can actually observe that there. But the next thing we're going to do instead is play a game. So we have 41,437 zip codes in our table. Which one's first? 00501. I can use sys.fn physloc formatter, which is a function that'll tell me the physical location of this row in the index. So I'm going to run that, and it's going to tell me that it is on file 1, because there's only one file, page 400, slot 0. Okay, that's the location in this index. Now, because this index is ordered by the values, if I change it to 99999, I'm going to get I'm going to move it, right? So if I run this again, I will see that now I am on page 488, slot 221, right? So I went from like page 400 to 488. And if I move it back to the original value, well, then once again, it will go back and be on page 400 there. So by changing the value, I'm moving the location of the row, right? Kind of like the guy who was moving in the picture. So what I'm going to do is I'm going to open another session, and I'm going to do this over and over again 5,000 times. Oops, that didn't copy. Hang on. Okay, so literally set it from 1 to 99999, and then set it back. And then I say, go 5,000, which means, repeat this 5,000 times. Now, while this is happening, I am going to count how many zip codes there are in this session, and I'm going to count it 1,000 times. So let me get this queued up and ready to go here. Yoink. All right, I'm going to start this, and I'm going to start this. And it should just take a few seconds here. Like 10 seconds or less usually. So hopefully it doesn't make a liar out of me. There we go. All right, so we have our results, and I can query the table that I dumped the results in, but it looks a lot better if we just aggregate. So here's the results. We got the right answer 60 times out of 1,000. We got one less, so we got an undercount 371 times, and we got a double count, or one more, 569 times. All right, so if you have data that's moving around, and you're using the default isolation level, you're getting the correct answer, in this case, 6% of the time. I will tell you it's usually more than that. But the idea here is you have undercounts and overcounts happening even with locking. There's nothing that's helping you here with that. Any questions before we move on? All right, so after read committed, the next level is called repeatable read. Okay, and you'll notice here now non-repeatable reads are not allowed, so that's why they called it repeatable read. This is the idea of if a query is repeated within the same transaction, records read the first time will not change. So once a row is locked to be read, that lock will be held for the length of the transaction, and it's any row that's read, even if it's a row that's not qualified as the results. If it has to scan to read it, well then guess what? Everything's getting locked, and that lock's getting held for the length of the transaction. These locks, though, will not stop additional rows from being added or included in subsequent queries. Okay, now if I were to try to show this with a picture, it'd be something like a front flash sync picture where we have a car that's moving, and it's really hard to see on this screen, but the flash fired, the car was moving, and it's still moving, and you can kind of see the shadow of it afterwards. The idea here is once the rows are read, they're locked now for the duration of the transaction. They're going to stay read and locked until the transaction completes or rolls back. Okay? But if we read a second time, if we issue a second statement within that transaction, new rows may in fact enter because they weren't locked. They didn't exist. We couldn't lock them. Okay? So I have demo for this as well. Okay? And what I'm going to show you very, very quickly here is if I have I'm going to look up all the cities in Illinois that start with the letter A. Okay? And there's a whole bunch, like 71 of them. Okay, if I look at the locks that are being held, well, there's a whole bunch of them. There's over 200 locks that are being held, again, because the transaction's still open, so it's holding those locks for the duration of the transaction. Okay, but phantom rows are still possible. So if we do this again, set to repeatable read, begin a transaction, and in another session, we add a new row, right? We can create a new row, a new city called like AAAAA, for example. That's able to complete just fine. And if I run this query again a second time within the transaction, it was able to get in. There's 72 rows there. So it's going to keep anything that's read from changing, but it's not going to prevent new things from being inserted. Okay? And that might be a problem. So to solve that problem, we have the next level, the most pessimistic level, called serializable. And this does not allow those phantom reads. So this builds on repeatable read, but it says if a query is repeated within the same transaction, the results will be the same, period. Right? So data that we saw previously cannot change, and also no new results can appear either. So now we have the problem where we need to lock data that doesn't yet exist. Right? And we do this with what are called key range locks. So the engine will take a key range lock, and these will prevent phantom reads by defining a range that other transactions cannot do anything, right? They can't even insert rows within. If you select a row or a range that doesn't exist, well, that gets locked too. So if we're selecting over a range, now everything's locked, whether we've read it or not. And actually, the first row outside the range is locked as well, the first key. That's to make sure nothing gets tacked onto the end. All right, now for a picture, you need a posed picture for this, right? People aren't moving, there's nothing that can happen. This is actually the most famous picture in the, or the most requested rather, picture in the US National Archives when Elvis decided to go visit Richard Nixon in 1970, I think. And they took this photo, but this was posed, nobody's moving, you know, you have no issues with anything blurring or anything like that. All right, so let's demo this real quick. Reset our database here. Once again, I'm going to create a unique index on the zip code column, and I'm going to set the serializable isolation level for this session. I'm going to begin a transaction, and I'm going to select all the cities with zip codes that begin with the numbers 1051. Now, since I told you they're a 5-digit number, there can be at most 10, of course. In this case, there's only 8. Right? So we have 8 rows that match our requirements. Now, because these locks are still being held, I can just query sysdm tran locks and see exactly what locks are being held right now. And if we look, here's what we have. We have request mode is range SS, which is a range lock. And you'll also notice there are 1, 2, 3, 4, 5, 6, 7, 8, 9 of them being held, even though there were only 8 rows returned in my result set. So it's using these key range locks to make sure that this data does not change and nothing else gets inserted into it. Okay, do we have any questions? Nope. Everybody good? All right, let's move on. So we're just done talking about pessimistic concurrency. Now let's talk about optimistic concurrency, right? And this is, we're going to try, instead of trying to use lots of locks, we're going to try to use row versioning to prevent issues. And we're going to take fewer locks, hopefully. So there should be less blocking because there's fewer locks. Readers will no longer block writers. Writers will no longer block readers. Writers will still block other writers, okay? And I have a picture here of a traffic circle. This is actually the town I grew up in. They got an 8-way traffic circle in the middle, because the traffic circle is kind of an optimistic way of managing traffic, right? You don't need a traffic light. You have people yielding and entering the circle and going where they need to go. And as long as there's not too much traffic, it usually works pretty well. And when you're in high school and you get your driver's license, you can drive around it as many times as you want. That was the game we always played. So in order to do this, we're going to use what's called the version store to keep track of all the different versions of the rows that may or may not be in play. And of course, the version store lives in tempdb. So the way row versioning works is whenever a row is updated, a previous version of that row is stored in the version store, and there's a pointer to it. So it's kind of like a singly linked list, if you're familiar with CS data structures. These versions are maintained for as long as an operation exists that might need them. So any version of rows modified by a transaction must be kept for as long as that transaction is open. So very quickly, if I had a table with 2 columns, ID and value, this might be our current version at time equals n. There may have been a previous version where the ID was still 6, but the value was 7, and maybe one even older than that, you know, where the value was 9 at time n minus 5. So you get this chain of different versions for each row that are held in the version store. This is kind of boring, so I thought I would do it instead with toy blocks. So I have a table here with 3 rows, and each row contains a toy block, and we have the time, that's the t equals value, and so because of this version store, we can tell what was going on at a certain time, right? The current state of the table is here, and I have it shown on the right there, but if we want to see a previous state, because we have these versions, right, at time equals 7, well, this is what the table would have looked like at that point. At time equals 4, it would have looked like this. We would have used those versions to do it instead. So we have these different versions that we can pull just based on what's stored in the version store and the time information that's kept in it. And the first isolation level that makes use of this is called read committed snapshot. Now, read committed snapshot gives you the same guarantees as read committed, but it's an optimistic implementation. So there's no dirty reads, but there's still non-repeatable and phantom reads. And this is what's called statement level snapshot isolation. So the query will see the most recently committed values as of the beginning of that statement. The transaction doesn't matter. So if you have you create a transaction and you do multiple reads within that transaction. Each one of those reads might return a different result if the data is changing on the back end. So to go back to our block example here, at time equals 7, this is the current state of our table. It looks like this. Let's say we start a read at time equals 7, so the statement is going to see this. Meanwhile, while that read is still occurring, we're going to insert 2 new rows, or we're going to update 2 rows rather, right? Now, because we're using read committed snapshot, the updater is not going to be blocked, right? The statement will be able to read the same version because of the version store, and the updater is able to actually update the values at the same time. So what the statement sees isn't going to change, which is great, and we didn't have to block anybody to do it because there weren't any locks being held on this. Now, to use read committed snapshot, you have to enable it. This is a different command. You have to use an alter database command, and when you enable it, it becomes the default isolation level for that database. So every other query will just use that instead. This command itself can block if there's other connections to the database. So usually when I deploy this, I make sure it's either a quiet time when nothing's going on, or during a maintenance window, or everybody's just okay with me killing everything. Pardon me. All right. So let's demo that. So under RCSI here, once again, I need to restore my database. And then once that's done, I'm going to enable read committed snapshot here. So that's our default now. There we go. Now, we're going to play that same game we played before where we move the rows around, right? So I'm going to open another session, and I'm going to change the values of the zip code 5,000 times. Whereas over in this session, I'm going to count 1,000 times how many rows there are. So let's start this, and let's start that. And once again, it should be done in about 10 seconds here. All right, there we go. Let's see how many rows there were each time now. Right, so by using read committed snapshot, we got the right answer 100% of the time. Right, the fact that this data was moving around wasn't phased because the version store was able to help us get the right result each time we counted. All right, so the final isolation level here is called snapshot. And this gives us the same guarantees as the serializable isolation level, but it gives us an optimistic implementation of them. So no dirty reads, no non-repeatable reads, or no phantom reads. Now, read committed snapshot was statement level. This is transaction level snapshot isolation. So a query will see the most recently committed values as of the beginning of its transaction, or the first time that data was read within a transaction. So before we could get different results each time, this time, as long as it's within a transaction, it will see the same thing. So, did my thing not work? Okay, hang on. My pointer is flaking here. Wait, there we go. So to enable it, we need to use a different command now. We need to say alter database set allow snapshot isolation on. This kind of like turns on the version store for this. But then we still need to specify in our application to set transaction isolation level to snapshot. You need to do both of these things to be able to use it. Now, because we have this transaction level isolation, we can get what's called an update conflict. So let me explain and walk you through this here. We have 2 processes. And let's say the first process reads data within a transaction but does not commit it, right? So it now has a snapshot that it's looking at. And anytime it wants to look at this data, it's going to look at the snapshot. Meanwhile, process 2 comes along, reads and updates the same data, but also does not commit anything. So now we have changes in an open transaction and a different snapshot that process 2 is looking at. And once again, it's an open transaction because it wasn't committed yet. Now, process 1's snapshot that was created first isn't going to see what process 2 just did, and it's not going to update it. It's just going to keep looking at its snapshot. If process 1 tries to update now, it's actually going to get blocked because process 2 has changes that are in the pipe, right, that are still not committed. And then what happens is as soon as process 2 commits, process 1 will actually error out, and you will get error 3960 on that process. So let's see how this works in a demo here. All right, so again, we're going to restore our database very quickly. And then we're going to allow snapshot isolation to occur. We're going to turn that on. We're going to switch over to the database, and we're going to actually define snapshot level isolation for this connection. So in this example, we're going to use a different set of data, but we're going to do the same thing. So we're going to begin a transaction. We're going to update our table, and we're going to set the zip code to 99999 for one particular city, a city called Hoopeston. It's in central Illinois. There's only one of them. And their high school sports teams are called the Corn Jerkers because they're in central Illinois. So they're kind of the butt of jokes if you live in Illinois a lot of the time. So we just set their zip code to 99999. Now, in another session, we're going to go over here. We're going to set transaction isolation level to snapshot, begin a transaction, and then select the data. Okay? Now, even though we have a change that went on in a different transaction in a different snapshot, of course, this hasn't propagated yet, right? Our change hasn't actually committed. Now, in this session, if we commit that transaction and check again, well, now it'll be right here. But if we go back to the other session, right, this still has a snapshot active. So it's still going to see the previous value because it's looking at its snapshot. It's not looking at the change that occurred and was just committed. Okay, let's commit this. And just to show you real quick here, the snapshot update conflict issue I talked about. So I'll do the same thing again. I'm going to begin a transaction. I'm going to read some data. So we have a snapshot that's created. Boom. We're going to pick a city, 60546, if you're curious. In another session, we're going to define snapshot isolation, and we're going to update that value. Okay, hang on, I need to delete a tab or two here. I wasn't doing those as I was going along. Should have cleaned up as I was going. Okay, so set transaction isolation snapshot, begin a transaction, and update that value. Boom, all right. This update succeeded because there was nothing to conflict with it, and there's an open transaction, so there's a snapshot sitting in this tab. Meanwhile, this tab has a different snapshot that happened because it was reading first. So we have two snapshots on the same data in play. One process has just updated those rows. Now in this session, I'm going to try to do an update as well. And what's going to happen here, and you got to kind of look in the corner, but you can see the wheel spinning down there. It's waiting, it's blocked. It cannot proceed because this data has already been updated and locks are being held to enforce that update until the transaction completes. So if I go to this other transaction, which opened first, and I commit it, this commit will succeed, right? No problem here. If I go back to our first one, you'll actually get an error that it failed because of that update conflict, right? Snapshot isolation transaction aborted due to update conflict, 3960. So the fact that you have this snapshot that each process can see that doesn't change as long as there's an open transaction can give you some advantages in terms of the data's not going to change, but if you have lots of updates that are occurring and run into this situation, you might have an update conflict you'd have to resolve either with a retry or something else in your application. Any questions about that before we finish up here? Yes? Is that not similar to a data lock? A deadlock. It kind of could be, I guess, but it's not. You don't have processes that have some of the locks they need and are waiting on locks of the others. It's just one has the lock at this point. So to me, it's not a true deadlock at least. Was there a question from online?
Yep. Does enabling snapshot isolation affect the size of TempDB?
Does enabling snapshot isolation affect the size of TempDB? Yes. Anytime you use the version store, it's going to be stored in TempDB. I'm not saying TempDB is going to be huge. That's going to depend on your workload. If you have lots of long running transactions, this might be an issue. But what I like to point out to people is this feature was introduced in 2005. Your hardware is faster, your storage is faster, everything is better and more improved since then. And it worked pretty darn well in 2005. So if you don't have lots of long running transactions and you're able to monitor and manage the size of your TempDB, this should not be an issue at all. Any other questions? All right, so with that, we're going to finish up here with just a few more minutes to spare. Everything I talked about today, I know I said SQL Server a lot. Everything I covered here behaves the exact same in Azure SQL Database and Azure SQL Managed Instance. and Azure SQL Edge. They're all the same engine. So whether you're working on premises or in the cloud or in a VM in the cloud or whatever, this is how this works. The exception will be that if you create a database in Azure SQL database, read committed snapshot is enabled by default. They made that change there because that was considered a new product, and they were willing to make, you know, what could be a breaking change. But if you spin up SQL Server in a virtual machine in Azure, or if you use managed instance, it will use read committed like the other versions. If you thought this was interesting and you want to read some more, Craig Friedman at Microsoft has some great blog posts on transaction isolation levels. Kaylin Delaney at Simple Talk wrote a whole book on locking, blocking, and row versioning that's really, really good. And Klaus from Austria actually has a really good blog post too, going through myths and misconceptions about transaction isolation levels. Again, if you want to see the session materials, go to sqlbob.com/dirtyreads or use this QR code, and you'll be able to get my slides, all the demo scripts I just showed you, the database I just used to demo. You can do this all and play with it on your own if you like. Everybody got that, so I can move to the next one finally. All right, and then if we have any more questions, again, feel free to reach out to me. If you need the feedback link, it is right there. And if there's any other questions, I'll be happy to take them right now. All right, I'll give you all a few minutes back then. Thank you very much. I hope you enjoyed.